Good afternoon, everyone. My name is Haoze, and today I'll be presenting CoFS, a file system designed specifically to accelerate container code startup. This work comes from Dr. Wang and colleagues at KylinSoft. So let's get started. So first, let's look at the motivation. Running application in container offers great scalability and portability, but the code start process is a well-known bottleneck. A container code start involves a sequential pipeline. So first, we download the image, we unpack it and configure it, and finally we start it. A landmark study by Dr. Harder at FAST16 showed that putting the image accounts for 76% of the total container startup time, yet only 6.4% of the put data is actually read during the startup. So the time spent on the unused data downloading may lead to a very high startup latency that may violate the responsiveness SLA in serverless computing or during the automatic scaling to handle the burst request. So to address this issue, several systems implement the on-demand putting, which is mentioned earlier. The container starts running before the entire image is downloaded, fetching the required data as is accessed. For example, the Nidus Fuse and E*GZ are the fuse-based file system level solution, but they inherit the Fuse 2 core cost. The first, every metadata lookup requires a round trip to the user space daemon and multiple context switching between the user space and the kernel space. And second, for the even already downloaded data will still be routed through the user space for reads. And another solution will be the Nidus Fuse that will, that avoids the use the fuse by modifying the in-kernel eropt to work with the FS cache. However, the data download would be synchronously write to the disk and notify the FS cache driver. Only then can the kernel serve it. Although the cache eviction is hard to control, causing performance fluctuation. And the last one will be the overlay BD, which operates at the block level, but that will prevent us from utilize the page cache sharing of image data across the containers. But Fuse is a very natural framework for on-demand putting, so we still want to keep using it while trying to mitigate overhead we mentioned in the previous slide. So let's zoom in on why Fuse can be problematic for the use cases here. There are two main bottlenecks. The first one will be the metadata lookup. Before reading any file, the kernel performs iterative path traversal for paths like the user local Bing app that will require 4 separate lookups. Each lookup will from the Linux virtual file system to the Fuse driver in the kernel space and switch to the user space daemon, and the user space daemon will get a response and send it back in the reverse order of this path. That means multiple context switches and the request copies per path component on the path. And second, even for the data that has already been downloaded and is sitting in the local host file system, Fuse will still forward the read request to user space for processing. So we are paying context switching and data copy overhead on every read, even for the cache data. So these two bottlenecks are what CoFS targets for. Here's the key insight that makes CoFS possible. The container images are built once with a fixed read-only file system here. The image layer are immutable, and that means 3 things. So first, the complete set of the file names is known at the image build time. And second, since the set is already fixed, so we can use a perfect hash function to pre-compute the hash value for all the entries for the image file. And third, after utilizing the hash function, we can achieve a one-time complexity lookup and no directory traversal needed at runtime. This is a fundamental observation that motivated the design of CoFS. So first, let's look at the minimum perfect hash function here. It's a hash function that maps m key to exactly 0 to m-1 inclusively with no collisions. And the figure here shows how we use the minimum perfect hash function in CoFS. On the left-hand side, we got an input key, which in CoFS is the concatenation of the parent inode number and the file name. And this key will get fed through the sub-hash function f1 and f2, producing 2 index A and B here, and then into the array G were pre-constructed. We look up those 2 positions by the index A and B and sum them modulo M and get a unique index HK. This index will finally be used to look up for the metadata of these files. The key properties that make these minimum perfect hash function attractive for the CoFS are first, it's collision free. Every valid key will map to a unique slot. And second is a space optimal with OM storage complexity. And third, that will give a O1 lookup time complexity because it's a hash function. And the last one will be the algorithm we use here will guarantee that the construction of the minimum perfect hash function during the image build is a linear time. So we can then integrate the minimum perfect hash function into our metadata file layout. We design the image format based on E*GZ. The key addition here is that we add a binary metadata file called CoFS inode array, replacing the original JSON format metadata. Its layout is shown here in the figure. The file starts with a fixed 12 bytes header containing a magic number and MPHF parameters. And following the headers are the three arrays that used in the minimum perfect hash function, T1, T2, and G. And the next comes is the true metadata array itself. Each element is about 120 byte file metadata entry containing all the metadata of the corresponding file for an inode. And if a file name is 16 bytes or shorter, it will store inline in the entry, or if longer, we will store in the last section, the extra metadata here. And the total space complexity will be OM, which is about 9.5 megabytes for a million files. Based on the minimum perfect hash function concept and the metadata file layout we just showed, we can now look at how CoFS put all these things together into its architecture. The CoFS consists of two main components. First, in the user space, we got a CoFNet snapshotter. It's implemented based on the E*GZ snapshotter. It's responsible for putting the metadata file, setting up the cache mirror directory, and serve as a fuse daemon that downloads the data on demand from the remote image repository. And second, we got an in-kernel space CoFS driver. It's an extended fuse driver, and it will handle the lookup request directly using the minimum perfect hash function. And for read requests, it will act as a gateway. It will request the data if the requested data has already been downloaded, meaning it exists in a mirror file on the local host file system, the CoFS driver will take a fast pass, which is shown at the dashed line here, and read it directly from the in-kernel file system. Only when the data hasn't been downloaded yet, it will fall back to the slow path with the solid line here. It will first contact the snapshot in the user space, just like the regular fuse did, and to fetch the metadata and the data from the image repository and turn it back to the driver and finally to the application. And we also noted, we should also note that we also make the snapshotter asynchronously write all the data it fetched from the repository into a mirror file into the host file system so that we can use it for the next read to using the fast path we just mentioned. So here, let's see how this layout enables the fast lookup process. The lookup process is to find the inode for a given file before actually we read the file content. First, we use the parent inode number and file name as a key, and we compute the minimum perfect hash function value based on the input, and then we will use the resulting hash value as an index to locate the corresponding element in a metadata array and read it from the metadata file. Next, we'll perform a verification. We will compare the parent inode and the file name length. If either doesn't match, or the file doesn't exist, if both the parent inode number and the file name match, the in-memory inode will be constructed from the entry we just read, and the entire process requires at most one I/O operation. And if the corresponding disk block is already in the page cache, no I/O is needed at all. Compare this to a traditional file system like the ext4, where I/O counts for the inode lookup without caching it depends on both the directory size and directory depth. Another problem we mentioned earlier would be the complexity of the path resolution. The Linux VFS will resolve the path top-down, one component at a time sequentially. For example, for the user local bin app, there will be 4 separate inode lookup in series from the root directory to the app finally. And CoFS built a second minimum perfect hash function here, keyed on the full file path beside the original minimum perfect hash function from the parent inode and file name we mentioned in the previous slide. And they both map to the same hash value for the same given file. At the runtime, when a file open operation is interpreted and the path exceeds 3 level depths, the CoFS will dispatch it into a kernel work queue thread. And the kernel, the worker will reserve the path bottom up from the bottom to the top, starting from the leaf, computing the full path minimum perfect hash function to construct the inode, and it will stop as soon as it hits one inode which is already in the memory. This works because if an inode is cached, all its ancestors are guaranteed to be cached too. This is because that at the same time, the normal virtual file system is resolving the same paths top down. They run concurrently and it will finally meet in the middle, cutting the serial lookup chain and thus improve the lookup performance. Now, let's look at how CoFS handle the data access after we know how to resolve for an inode here. And when an application reads the data that hasn't been downloaded yet, here's the flaw. It's uncached data rate. The read request comes from the application, go through the union file system and reach the CoFS driver. The driver will check the mirror file pointer of the inode is none or not. If it's none, it will check whether a mirror file exists in the mirror directory. If in this case, the first time exists, we're talking about the uncached data, which means the data is accessed for the first time. There will be no mirror file because we haven't downloaded yet. And the corresponding range within the sparse file would contain a hole. So the CoFS driver forwards the request to the snapshot in the user space, and the snapshotter will fetch the data from the remote image repository and return it to the driver, which passes it back to the application. And after returning data, just like I mentioned when introducing the architecture, the snapshotter will asynchronously write to check the mirror file directory. If no mirror file exists, it will create an empty sparse file, then asynchronously write the fetch data into the corresponding range of the mirror file so that we can use the fast path next time. And here is a fast path. This is designed for the cache data rate. The request will still flow from the application in a container and through the union file system to the CoFS driver here. And this time, we will check for the cached mirror file, and that will return a valid mirror file pointer. So when all the data requests in the mirror file without any host, that the driver would directly read the mirror file through the host file system. Notice that the CoFS snapshotter is not touched at this time, and the image repository, we didn't contact the image repository here. So the data read happened entirely in the kernel space. There will be no context switches for the CoFS driver here. Now is the time for the evaluation. We evaluate the performance on configuration intentionally to simulate the limited download bandwidth for remote shard image repository. We measure code startup time across 4 commonly used container images: MariaDB, Redis, Tomcat, and Elasticsearch, and we only show 3 of them here on the slides due to the space limitation. The results are clear. The CoFS outperforms all the system and library container tested. And one interesting we noticed when performing this evaluation is that when a system downloads the rest of the image in the background when the code startup, that will actually degrade the performance in most cases. For example, if you look at the figure here, the column that in the figure ending with a -p is with the background download turned on. And the reason that the entire image is much larger than the data we try to access during the startup, so the effective background download will compete for the local network bandwidth and I/O resource and finally harm the performance. Also, we noticed that the Nidus erofs here is worse than the original Nidus fuse in some scenarios. We think that would be due to the long FS cache call chain inherited in the Nidus erofs. And also, for the lookup performance specifically, we measure the execution time of the fuse lookup function during the container startup. Compared to a simple fuse-based lookup system, fuse lookup, the CoFS achieves 73 to 86% improvements in average lookup time across all containers. And the parallel lookup optimization contributes an additional 28% improvement of the container images with deeper directory structures. For the cache data rate performance, the results show that the kernel space system, including CoFS, all achieve nearly identical bandwidth and latency because they all access the download data in the kernel space. And for the fuse-based solutions like the Nidus Fuse and E*GZ, they perform worse because they still wrote the cache data read through the user space fuse statement. And about the minimum perfect hash function construction overhead side, the minimum perfect hash function construction time scales linearly. And given that the building an image at a large scale takes at least several minutes, we think that it is negligible and acceptable. So to summarize, CoFS make 3 key contributions. First, the minimum perfect hash function based lookup. By pre-computing a minimal perfect hash function at image view time, CoFS achieve O1 metadata lookup directly from the kernel space, requiring at most 1 I/O operation and completely avoid the user space round trip. Second, a kernel space fast path for data access. The sparse mirror files on the host file system incrementally cache download data, and cached read are served entirely in the kernel space with no fuse overhead. Third, parallel data resolution. A second minimum perfect hash function keyed on the full file paths enables a kernel worker thread to resolve INO bottom up concurrently with the VFS top down traversal. This results in that the CoFS outperforms all the state-of-the-art on-demand pooling system we mentioned, with 73 to 86% lookup improvement over fuse. Thank you, and I'm happy to take any questions.